Now we're ready to look at a whole series of organic acids, and there's really two reasons that we give you this information. The reasons we give you these are to familiarize you with the various functional groups that we'll encounter in organic chemistry. We don't expect you to memorize this list, but by writing out, and we do encourage you to write out each of these chemical dissociation, acid dissociation steps, but by writing out this data, writing out these equations, you'll familiarize yourself with the acid character of the different organic functional groups. Secondly, with this data, so let's begin to go through this list. We won't go through every step in detail, but you'll need to look through this list on your own and go through it. We begin by what is the strongest of the organic functional acids, the functional group, the nitro group, in its protonated form, is really one of the strongest functional groups that there is in organic chemistry. Consequently, the conjugate base of that is the weakest base that we'll encounter in organic chemistry. It's extremely difficult to protonate the nitro group. So the dissociation constant, the pKa, has a funny value. It's minus 11.3, and just remember, according to the definition, that means that the dissociation constant is extremely large. It's very highly favored. This is an equilibrium that's almost certain to lie to the right unless we have a very, very strong acid that's present that could protonate the nitro group. The very small numbers are in pKa reflect the very strongest of the acids. What you see next, I won't go through in great detail, but you'll see the nitrilium ion. That's the protonated form of the nitrile group. The protonated ketone, which of course is a very important intermediate, and we can see it showing up on the list relatively early, meaning that it's a very strong acid. And then finally we encounter a sulfur-containing functional group, the thiol, in its protonated form, the sulfonium ion shown here. Pay attention to these oval circles as they represent the first time that atom type in a particular hybridization state is encountered. So for example, with the nitrile, we see that this is the first time we encounter an sp hybridized nitrogen bearing a positive charge. In the case of the ketone, this is the first time we encounter an oxygen positively charged, sp2 hybridized, and so on and so forth. Also notice these ovals are the first time we encounter it without any effects of delocalization. So where delocalization is unimportant. And so what we're going to do in the following webcast is to collect all of these ovals and be able to separate out the effects of hybridization and atom type, and we'll see some important trends that will emerge. And I will encourage you to go ahead and collect that data as you work through this. The other thing to notice is that all of these acids that we first encounter are type 1 acids, and those are the cations that are trying to get rid of their proton, and later, at the very end of the list, we'll encounter the type 1 acids. Now, that's not a hard and fast rule. Somewhere in the middle, we'll encounter mixtures of type 1 and type 2, but at the beginning is type 1, at the end is type 2. Finally, let me just benchmark this set of organic acids, strong organic acids, with something that you are familiar with. So the pKa of HCl is about -7. So that's concentrated HCl, pKa -7. In other words, it has enough proton power in HCl to protonate a carbonyl to a significant degree, and less so to something like protonating the nitrile group or the nitro group with just HCl alone would be relatively an equilibrium that would lie pretty much to the side of HCl and the conjugate base of these organic acids. We need something more. We need a stronger proton source if we're going to protonate the nitrile or the nitro group. All right, let's move on. Moving through this list, there's one more important concept that we need to encounter before we move all the way to the end of the list and look at the very weakest of the organic acids. So when we get to the ester, what we see is a choice has to be made in terms of which of the atoms we're going to add the proton to. In the case of the ester, do we protonate the oxygen that we would typically consider, if we don't take resonance into consideration, the sp2 oxygen, or would we protonate the lone pairs? Remember, there are two lone pairs here. Would we protonate the lone pairs on the sp3 oxygen? where does the proton add? Well, it turns out that in spite of the fact that we learned about charge stability and positive charge would rather be on sp3 than sp2, there's another factor that we'll see weighs in to protonate, to favor proton adding to that sp2 oxygen. And this is a very general trend. Anytime we have the possibility of spreading that charge around by delocalization, in this case an N to pi star type interaction, pi star being very much lowered by that positive charge on oxygen, we have an important resonance contributor that helps to spread that charge over two atoms. Being able to spread charge over two atoms is definitely an important factor that contributes to stability of a charged species. And you'll see in just a moment that we could not have spread that positive charge over both oxygen atoms had we protonated that what I was referring to as an sp3 hybridized oxygen. So here, by protonating the sp2 oxygen, we have the important conclusion that we can share that positive charge on two atoms. Had we protonated that sp3 oxygen, we would have ended up with a structure that had no chance for delocalization. The positive charge would have been exclusively residing on one atom, and there isn't any way to spread that positive charge. There is no delocalized forms of importance in that when the proton has added to that oxygen. And so even though it's an sp3 oxygen, what we learn from this lesson, this example, teaches us an important lesson, and that lesson is when delocalization is an option, we'll take the proton adding to an atom that is less favorable from the hybridization standpoint in order to share that positive charge or negative charge, as the case might be, over multiple atoms. Delocalization is important. It may even be more important in most cases than the hybridization, the role that hybridization plays in contributing to the stability of charged species. You'll see this encountered in numerous times throughout the list, that the preference for adding a proton is to the atom that can facilitate charge delocalization. So keep that in mind. It's a very important point. Let's jump all the way to the end of the list, where we start to encounter acids of, we've all, in this case encountered now, acids of type 2, a neutral species dissociating to an anion, and these are the most difficult dissociation events to take place. So dissociation of that vinyl hydrogen to make the vinyl anion, the pK is very large, very positive, meaning that acid dissociation constant is a very small number. That equilibrium lies all the way over to the left. Minus 44 in the case where we encounter putting a negative charge on an sp2 hybridized carbon, and if we were to put that negative charge on an sp3 hybridized carbon, which is not able to stabilize that charge, we see that the pK drops off another 6 orders of magnitude in Ka dissociation constant.